Hi, welcome to College Algebra. So this is our first content video, and what you'll want to do before watching all of the content videos is you'll want to go to D2L in the content area and print out the lecture notes. So if you print them out and then you can watch these videos and take notes on top of the lecture notes if you need to. And you can use the back or a different sheet of paper for some of the longer problems if you need more room, but most of the time you can just print out these lecture notes and write on top of them, and that'll save you a whole lot of writing. So we're going to start with the prerequisites chapter. So we'll do two classes essentially on the prerequisites chapter. So this is everything that you should know before college algebra. It's the stuff from pre-algebra, algebra 1, and algebra 2 that lays the foundation for college algebra. So we'll go faster through these things. I'll mention them, but there will be an assumption that you have seen this material before for sure. And so we'll start with what numbers are. So real numbers, which is what we will primarily be focusing for the whole course, we'll be focusing primarily on real numbers. And real numbers include all of these numbers that you see right here, and of course more because you can't list them all. Natural numbers are also known as counting numbers because we count them. So you would start with 1. You would do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then you would keep going forever and ever and ever. And those are natural numbers. If we wanted to describe whole numbers, that would be all of the natural numbers plus 0. 0 is not part of the natural numbers, but it is part of the whole numbers. And you'll notice that all of these are positive, and that's going to always be true. If we want to add in negative numbers, then we call those integers. So that we're growing in our sets here. So the set of integers includes all of the negative values in addition to the positive values and 0. And then if we wanted to include decimals or fractions, we would go to rational numbers. So anything that can be expressed as a whole number over a whole number or an integer divided by an integer is what we call a ratio or a rational number. And it can also be expressed in decimals. Sometimes it's expressed in repeating decimals, like 2/3 would be 0.6 repeating. But if there isn't a repetition in the numbers when you do the decimal expression, then that's what we call irrational numbers. So if we take the square root or even cube roots, or you see the fourth root here, of numbers that aren't perfect squares, or in this case, that aren't perfect fourth roots, or if we have pi or e is another one, like e equals mc squared. E is an actual number as well, and all of those are irrational numbers because they can't be expressed as decimals that stop or decimals that repeat. So those are the rational numbers. And really, all of these decimals can be expressed as the ratio of an integer divided by an integer. So if it can't be expressed in that, then it's not a ratio or irrational. And then when we use notation, we will use this notation throughout the course. A lot of times, textbooks will have like a closed circle instead of this closed bracket, but this textbook uses closed brackets, both on the notation and on when they draw it on the number line. So when you have a closed bracket, what that means is that A is included, and that's why it's less than or equal to A, or actually X is greater than or equal to A, and B is included, and so that's why X is less than or equal to B. So whenever we see these brackets, these closed brackets, that means you do include A and you do include B. So let's say it was bracket 3 comma 4 closed bracket, then it would include the 3 and it would include the 4. On the other hand, if you see these open parentheses, that means it does not include that number. So you're talking about all of the numbers that are between these two values, between, for example, 3 and 4, but it doesn't include 3 and it doesn't include 4, for example. Now, if you've got a bracket on one but not on the other, then it includes the one that's closest to the bracket, but it does not include the one that's closest to the other. So it goes every value that is strictly more than A. So if A was 3, it would be like 3.1, 3.01, 3.0000001 would still be included, but 3 itself would not be included for this interval, for instance. 4, however, would be included if it was 3, 4, with the closed bracket on 3 and the open parenthesis on 4. So that's how these work. And then when we have infinity, that means it's going to go forever in the positive direction for positive infinity. If we have negative infinity, that means it's going to go forever in the negative direction. And infinity is not an actual value, it's a concept. So there is no number that is equal to infinity. If you take the highest number you think of, infinity is a value that, or is not a value, but it's an idea. Infinity would be more than that value. And so for that reason, we can never equal infinity. So we'll always have the open parentheses. Whenever we have positive infinity or negative infinity, it will always be the open parentheses. But when we're expressing it in the drawing on the number line, it will just be darkening the arrow in that direction. And so here we want to describe the set of real numbers, the subset of real numbers for these three examples. So x less than or equal to 2 means that we include 2 and we include all numbers that are less than 2. So when we do this, we would basically shade everything that is less than or equal to 2, and you see that we have the closed bracket to denote that it is 2. It does include 2. So all real numbers that are less than or equal to 2. Now here we're greater than and we do not include. So for B, we are greater than and we do not include. So when we look at B, we would shade everything that's greater than -1. And we do the open parenthesis to denote that we do not include the -1. And then lastly, between -2 and 3, it does include -2, but it does not include +3. So on the number line, we would do everything between -2 and +3. We would not include 3, and we would include the 2 there. And then here are some more examples. So we want to use inequality notation. And again, here is our inequality notation to represent C is at most 2. And I like to think of the number line too when we do this. So at most 2, so does it include 2? Yes, it does include the 2. Does it include 3? No, it would not. What about 1? Yes, it would include the 1. So basically, we're going to go this direction and include everything that is less than or equal to 2. And that's how we get there. So less than or equal to 2. And then everything that's between -3 and 5, that's going to be, when we do that, that will be x is between -3 and 5. We do want to include 5, So that'll be less than or equal to 5, but we do not want to include the -3, so it's strictly going to be that x is more than the -3 or between the two, but not equal to. And then at least 4, so that does include 4, but less than 11. So again, it's between 4 and 11 that we would have here. Strictly less than 11. At least 4 means that it could be 4. And you'll see these on the number line. If you draw the number line as well, you can see these more easily. And then we want to give a verbal description of each interval. So for this, we would have all of the numbers between -1 and 0, but not including -1 and not including 0. And then for this one, we would have all of the numbers between 2 and infinity, which is essentially all of the numbers that are equal to 2 because equal is included, and all of the numbers that are more than 2, every possible number that is greater than 2 or equal to 2. And then for this one, this would be all of the numbers that do not include 0, and of course don't include negative infinity, but are between the two, between negative infinity and 0. And really that's every possible negative integer is a succinct way of describing that. Because you've got to be negative if you're going to be less than 0, and you aren't including zeros. And then here are some properties of absolute value. Absolute value, this is the symbol for the absolute value of A. And so when we do absolute value, what we're essentially saying is that we're removing the negative sign because it's really used for distance, and we never talk about negative distance. We only talk about it as no distance, which is 0, or positive distance. So the absolute value strips the negative sign off, so that's why it's always going to be greater than 0. If we have A, we don't know if A is positive or negative itself, but we know that if we take the negative of A and we take the positive of A and we do the absolute value of each of those will end up being equal. And if any of this ever gets confusing, because today we're going to talk about a whole bunch of these rules, then what you should do is you should say, okay, let me put a real number in there. So what if A is 2? Well, -2, if I take the absolute value of -2, I get 2. 2, if I take the absolute value of 2, I get 2. Those are equal. 2 is equal to 2. So just stick some real numbers in A and B, and all of these properties have been true since elementary school when you first started thinking of the concept of absolute value. So even though we're using letters, which you probably didn't start doing until middle school or high school, these have been true since elementary school. And that will be true of pretty much all the properties that we discussed today. Not every single one maybe is an elementary school concept, but it almost all of them are, except they're applied to letters, and then almost all of them are going to be pretty straightforward. It's just that you don't remember them. So spend some time with these. If we do the product of two numbers that are under one absolute value, then it turns out that we can separate them and they will still give us the same thing. The same thing is true of division. If we have a fraction under the absolute value, then we can separate those values, both under absolute value, and still get the same thing. And so here, if we are asked to evaluate any expression that has an absolute value in it, we are often going to need to do that in two cases. Case one will be whenever the value is positive, and then case two is whenever the value of your variable is negative, or really not even your variable, but the stuff that's under the absolute value. If the value of the stuff inside the absolute value is positive, then you'll want to do one case, and if it's negative, then you'll want to do another. So this is really our case one, and this is really our case two. And so we're saying, okay, what if the stuff is positive? Then if it's positive, I can remove the absolute value and I'm just going to have x. But if it's negative, I can remove the absolute value and I'm going to have the negative of the stuff. And that's what we're going to do every single time we have one of these expressions with absolute value. We'll break it into cases. Removing the absolute value if the stuff under there is positive is not going to change it. Removing the absolute value if the stuff under there is negative is going to be the negative of all that stuff under there. So every single time we do that, that's the process that you're going to want to do. And then we just have x divided by x is 1, and we have negative x divided by negative x is negative 1. So that's how we'll work those types of problems. Now, the distance between 2 points on a real number line, here we have the distance between -3 and +4. And we can either do it as b minus a or a minus b, because we're always, always, always going to take the absolute value whenever we do distance. So distance between two numbers, we will do the absolute value of the two. So it really doesn't matter if we do 4 minus -3 or if we do -3 minus 4. Because once we do the absolute value of those things, we will get 7 both times. And then here are lots of other properties. And you may be thinking, oh my goodness, I don't remember the commutative property and the associative property, the distributive property and the additive identity. You don't have to know all these names, but just know that you're allowed to say that 2 plus 3 is the same thing as 3 plus 2, right? We've done that all our lives. 3 times 2 is the same thing as 2 times 3. You're allowed to switch it around. 2 plus 3 plus 4, we could add the 2 and the 3 together and then add the 4, or we could add the 3 and the 4 together and then add the 2. We're allowed to do that. That's the property of association. You don't have to know that's the property of association. You just need to know that the order doesn't necessarily matter here in which you do the addition. And the same thing's true with multiplication. 2 times 3 times 4. You can do the 2 times 3 first, or you can do the 3 times 4 first. Either one, 2 times 3 first or 3 times 4 first. You're still going to get the same number. And then the distributive property, if you do 2 times 3 plus 4, order does matter here. You have to do the stuff inside the parentheses first, or if you don't know how to combine the stuff inside parentheses, then you distribute, and that's why it's called distributive. You distribute the a to both things. So it's now a times b plus a times c. And here we're distributing the c to both things, really. So we have a times c plus b times c. And then the additive identity is 0, because you can add 0 to anything and you're still going to get that original thing. So that's just what that's saying. So 2 plus 0, 3 plus 0, 4 plus 0, we're going to get back 2, 3, and 4. A plus 0, we're going to get back A. The multiplicative identity is going to be the thing that you can multiply any number by and still get that original number, and that's going to be 1. So you can multiply any number by 1, think of any number that you can think of, and if you multiply it by 1, you're still going to get that original number. So when you do it with letters, you're still going to get that original letter. The additive inverse is basically taking a number and sticking a negative in front of it, whether that number is already negative or not. So the negative of -2 is going to be +2, in other words. So if you take -2 and you take +2 and you add them together, you're going to get the additive identity of 0. So these are called additive inverses because they undo each other. So you can add them together and you get nothing. The multiplicative is going to give you the multiplicative identity, though. So if you have a number and you multiply by its reciprocal, in other words, 1 over that number, you're going to get 1. So you can kind of undo multiplying by multiplying by 1 over a, because that's the same thing as multiplying by 1. So all of these properties are true. Hopefully they seem pretty familiar to you. And so for these properties, for instance, if you take any value like a and multiply by -1, you're going to get negative a. And if you already have a negative value and you multiply by a negative, you will get back positive a. Again, this is exactly the same way it works with real numbers. As a matter of fact, most of our examples you'll see are with real numbers. So just think of sticking real numbers into these, and hopefully all of these properties will make a lot of sense. And if you get lost in the algebra and you get scared of the algebra, think, well, what if these were real numbers? How would they work then? So this is all exactly the type of stuff that we've been doing in mathematics forever and ever. So if we have a negative and a positive together, we can multiply those two numbers together and stick a negative in front of it. And then if we have a positive times a negative, again, it's the same thing. It's going to end up giving us the negative of whatever AB is. But if you've got two negatives together, two negatives multiplied together always give you a positive. So two negatives, that will give you a positive. If you've got negative out here, though, we're going to kind of distribute that negative. So it's essentially like saying this is -1 times the a plus b. So that's negative a plus negative b that we have there. If you know that A equals B ahead of time, then it turns out that you could have like C equals C, and you could say, okay, I'm going to add A to this and I'm going to add B to this, and I haven't changed the values because I know that A and B are equal to each other. Also, you can add C to one side as long as you add it to the other. You can multiply C by one side as long as you multiply it by the other. So there's the property in mathematics, and it carries over to algebra, that whatever you do to one side of the equation, as long as you do it to the other, your equation is still going to remain equal. And that's really what 6 and 7 are showing us. Also, if we know that A equals B, so we have originally the A and the B, we can add or subtract. And that's kind of what we did up here as well. And then if we, as long as C is not 0, we could, divide both sides by C, essentially, and that would end up canceling these C's out. And when we do that, we would get A equals B. So that's true as well. And then properties of 0, we can add 0 to anything and it's not going to change what we have. We can subtract 0 from anything and it's not going to change what we have. If we multiply any number, any real number by 0, we're going to get 0. If we have 0 divided by any real number, assuming that number is not 0 itself, because we're not allowed to divide by 0. Dividing by 0 we call undefined. But if we have 0 divided by any non-zero number, that's always going to give us 0. And then if we know that A times B equals 0, that means one of them has to be 0. Either A has to be 0 or B has to be 0, or it could be both as well. And then we have lots of more properties. Again, all of this stuff applies to real numbers. So this has always been true. All of this stuff has always been true. This is, I don't know if you remember it or not, but this is kind of cross multiplying. So if you have a fraction is equal to a fraction, then you can cross multiply, is what we call it. And so what that means is that A times D is equal to B times C, and that's always true. And we could tell you why that's true, because if you multiplied both sides by BD, um, what you do to one side, you have to do to the other. You can multiply both sides by BD to get rid of the B in the denominator and the D in the denominator. And when you simplified everything, you would get AD equals BC. So that's why that's true. And then if you have the negative of a fraction, it could be that the numerator is negative or the denominator is negative, so that all those things are equal. If you have a negative numerator and a negative denominator, those end up canceling each other out, and that's equal to having the positive of that value divided by the positive of that value. You can multiply C over C, because that's 1, and multiplying by 1 doesn't change anything. So you can multiply any fraction by C over C as long as C is not 0, because again, we're not allowed to divide by 0. And then if you're adding two fractions together, and again, this was true all the time, if you're adding two fractions together, you want a common denominator. You want the bottom part to be the same. And then once you know that, you just add or subtract the top part. So you can combine the fraction by adding or subtracting the numerators together and then having that common denominator. And if you don't have the common denominator already, you can make one by multiplying this fraction by d over d and this fraction by b over b to get them both to be bd. And so that's going to be AD times CB, because we did multiply that. So that's always going to be true. And then multiply fractions together. Here, when we are multiplying fractions, we multiply both the numerators and the denominators together. So that's different from addition. Addition, if you had a common denominator, you would not change the denominator, you would just add and subtract the numerators. But on multiplication, we multiply both the numerators and the denominators together. With division, whenever we have a division symbol, we will do what we call flipping and multiplying. So let me make that. So here we will change this, but we have flipped the fraction. So now instead of C over D, it's D over C. And we're allowed to do that as long as all of the stuff in the bottom is not 0. So as long as C is not 0, we're allowed to do that. And then we have the fundamental theorem of arithmetic. So this sounds important, and it turns out that it is, but you don't have to memorize it. Just realize that a lot of times, especially if you're trying to find a common denominator, but a lot of other stuff that we will do for this course, you will want to know how to break down a number into all of its components. So 24, I think of it as 6 times 4. But 6 can be broken down into 3 times 2, and 4 can be broken down to 2 times 2. So essentially, this is the prime factorization, and really that's what that says right here, except it's just in a different order. So breaking it down into prime numbers are numbers that cannot be further broken down. The only factors are itself and 1. So that's the definition of prime numbers. And then here any expression, these are all expressions. So they're kind of like one part of an equal sign on an algebraic equation. So you can think of it just as like stuff that's algebra that doesn't have an equal sign on it. Those are all called expressions. And then of course the variables are the letters that we'll use. X is the most popular one, followed by Y and Z, but we can use A, B, and C, and we can use Greek letters too. We just don't normally use Greek letters for algebra. And then to substitute to work algebra, we can say, well, if we know X is 3, we just plug in 3 everywhere we see X. And if we know X is -1, we just plug in -1 and do the arithmetic everywhere we see X. And here we see x here and here, so we plug in -3 here and here, and that's the way algebra will work. And then we just simplify that to get the value of the expression. And here are some examples. And we already talked about how we can, if we have a fraction, we can multiply that fraction by the same thing in the numerator as in the denominator, and it's not going to change that because 3 divided by 3 is just 1. So we're essentially multiplying by 1, which does not change the value. So here, x divided by 5 is the same thing as 3x divided by 15. Think of x as 1. 1/5 is the same thing as 3/15. It's just simplified. And 2/4 is the same thing as 1/2. It's just simplified. So if we divide, though, remember we want to flip and multiply. And so this expression is the same thing as this. And then we multiply the numerators together and the denominators together, just like our previous rules told us we could do. And that means that we'll get 7 times 2 is 14, and x times 3 is 3x. And so these are following some of the basic rules of algebra. Now we have rules of exponents, and you would have covered these too. Maybe not in elementary school. It's hard for me to remember when these are first covered, but certainly in middle school you would have seen some exponents, and in high school you would have seen some exponents. A lot of these examples are with real numbers. So again, plugging in real numbers to understand why these properties are true will help you remember that these properties are true. So anything that you're allowed to do with actual numbers in place of the letters, you're allowed to do when you put letters there as well. So here, notice that we have A like in both places, everywhere. So as long, we call A in this case, we call it the base because it's the bottom part, and the M and the N are the exponents, that's the top part. So here our bases were all the same. So our A's are all the same everywhere. That means that we can add these exponents together. So we have A to a power and A to a different power. We can just add these exponents together. We're allowed to do that. If we're not multiplying, but because these two are multiplied by each other, if we're instead dividing, then that means we'll end up subtracting the exponents. And actually, we can move exponents around from top to bottom by making that a negative symbol there instead of a positive symbol. So if you have 3 to the negative second power, for instance, or even 3 to the negative first power, then that's just going to be 1 over 3, or 1 over 3 squared if it was to the negative second power. And you can also move the power outside of the, like have it be 1 over a to the nth, because that would be 1 to the nth divided by a to the nth, and 1 to any power is just going to be 1. So that's true. And then a to the 0th power, any number to the 0th power is by definition going to be 1 as long as it's not 0. 0 to the first power or 0 to the 0th power is not defined. 0 to the first power is 1. 0 to the first power is 0, but 0 to any power other than 0 is 0, but 0 to the 0th power is not defined. And then if we want to have outside of parentheses raised to a power, then we distribute that to the A and to the B. So that's how we get that. If, though, we have a power raised to another power, then instead of adding those powers, because here we added those powers together when we had the same base, but different exponents. But here, if we have the number, it's raised to one power, and then it's raised to another power, we multiply those together. So, for instance, if we had a to the second power, and then raised to the third power, that would be the same as a to the sixth power. And then if you have a fraction that's to a power, you can distribute that just like we did in number 5. So we distribute that to the top and the bottom. If we have absolute values, then and we have even powers, then those do the same thing, because anytime we have a times a, anytime we have a pair together, it doesn't matter whether a is positive or negative. That pair is a negative times a negative is always going to give us a positive, and a positive times a positive is always going to give us a positive. So anytime we squared it, or any even power, that's the same as an absolute value, because you're guaranteed to have a positive number. So these are all identical. And then what's not true, and this is one of the most common mistakes that students will make, so I definitely want to warn you about this one. What's not true is that -2 inside parenthesis raised to the fourth power is the same thing as negative of 2 to the fourth. If you do this in your calculator and you don't put parentheses around the -2, then your calculator is going to take 2 to the fourth and then stick a negative sign in front of it, which is exactly what it does here. And that's the right thing to do, because this is a different expression than this one. This one is saying -2 and raising it to the fourth power. This one's saying raise the 2 to the fourth power and take the negative of it. So be aware that these are very different. And please, please, please remember, if you're dealing with negatives inside your calculator, and it looks like this, you better put parentheses around it in your calculator to get the right answer. So here, let's do some examples. And these are the properties that we've already gone over before, but just to have them referenced there. And if we do this, we want to do -3 times 4. That should give us -12. And then a times a, that should give us a squared, because again, we're adding these exponents. And even though I'm circling that there, maybe I shouldn't have circled that, the assumed exponent, if you don't have one, is 1. And I was kind of circling that 1, but it made it look like it was a to the 0th power. That's not what I meant to do. So that's why I rewrote it. And then 4 times, or 4 plus -3, because we're adding those exponents together, that will give us to the first power, or we could just write it as b. So this would be how we would combine this one. And by the way, I haven't said this yet, but if you have questions as we go through and as you're taking notes, mark those on your paper and ask them in the beginning of the hybrid class. So for the hybrid class, when we come together, you just mark all of the things on your paper, and we will start class with like a pull everywhere I'm here question. But as soon as I launch that, I will take questions from you. And so if you have questions about why any of this stuff was true, and you want more detail, just ask me in class. So you may want to have a highlighter and highlight the parts of your notes where you wanted to ask questions. And if you have questions about stuff that is outside of class, or if you're not in a hybrid class, then you can message me either via text or remind. Just send me a remind message and I'll answer those. So then on this next one, for 2, for raised to the third power, all of this raised to the third power, we're going to want to distribute the third to everything. So this becomes 2 to the third times x to the third times y squared to the third. And when we do that, 2 to the third is going to be 8, and then x cubed, and then remember, a power raised to another power, we actually multiply those together, and so that's going to be y to the 6th power. And so that will be our answer there. And then if we have anything raised to the 0th power, then that stuff just falls out. As long as this stuff is not 0 itself, and we're going to go ahead and assume that negative 4a squared does not equal 0, which essentially means that a does not equal 0. Because if we divide both sides by negative 4, we would get a squared does not equal 0, and a squared, the only way a squared could equal 0 is if a equals 0. So really, all of this stuff becomes 1, as long as a is not 0. And so that means that our answer is 3a, again, where a is not 0. So hopefully that makes sense. And then here are some more examples. And we're told that x to the negative first power is going to be 1 over x. And hopefully that makes a lot of sense because we have this third rule, and if our n was 1 and our a was x instead of a, then that would be true. So hopefully that makes a lot of sense. And then I think it did B and C because it wanted you to realize the difference between having the x to the negative 2 without parentheses and then having the 3x in parentheses and then the negative 2. So here on this one, we want to move the x to the negative 2 to the top because we want to get rid of that negative exponent. And so when we move it to the top, the exponent becomes positive. If it were negative in the top and we moved it to the bottom, it would also become positive. So we're allowed to do both of those things. And that's really rule 3 as well, that we're allowed to move it back and forth. And then 1 times x squared is just x squared, so our x squared over 3 is the answer here. We get a different answer for C, though, because, again, we've got to distribute this negative. So we essentially get, if we move the whole thing up, so the whole 3x up to the top and get this, and then we can distribute this. Or you could distribute first and then move each of them up. So the 3x squared, that becomes 3 squared times x squared, and then that's 3 squared is the 9. So 9x squared is our final answer there. And then for this one, we want to move the negative exponent stuff. So b to the 4th gets moved to the bottom, and a squared would get, or a to the negative 2 would get moved to the top and become a squared. And this b to the negative 4th becomes b to the 4th as we move them around. And then we combine like terms. So b understood to be the first power, and then a cubed times a squared. The 12 divided by 4 becomes 3, and the 3 plus 2, sorry, is equal to 5. And again, the understood to be 1, so it's understood to be 1 plus 4 is also 5. And so that's what it looks like when we are through simplifying and combining like terms. And then we have, we want to distribute the negative squared. So we really are flipping this, right? So if it's negative, that means we flip it. Oh, actually, that's the first step I would have done, but that's not what they did. So let's go through what they did. They went ahead and distributed the negative 2 everywhere. So this x squared gets raised to the negative 2, and the y becomes negative 2. And then they dealt with this, and so that you're going to multiply the exponents together, and that gives you the negative 4th, and then they're going to hopefully, yeah, here they flip everything eventually, and so when we move the y to the negative 2 in the numerator, it becomes positive 2, the 3 to the negative 2, the denominator becomes positive, and the x to the negative 4 to the denominator, it becomes positive. And then we say 3 squared is actually 9, and so that's our final answer there. And again, we're using all of this stuff that we've been talking about to do these. Now, that is pretty much all of that little section there. Moving into the scientific notation section, this section will be a lot shorter, not nearly as many rules to follow. So basically, if you have a ton of zeros, whether it's a ton of zeros after a number but before the decimal, or a ton of zeros after the decimal but before the number, so this is a really large number and this is a really small number, all these zeros are really just placeholders. So what it's saying is that you can move the decimal. If you move the decimal to the left, so the decimal is understood to be here, and you're moving it to right here between the 3 and the 6, when you do that and you've moved it 20 places, the exponent is positive. So we write it as scientific notation. So 3.66 times 10 to the positive 20th. And by the way, your calculator will do this. It will write it as 3.66. It'll probably usually give some more numbers. And it will say e to the 20. And that's shorthand for this stuff right here. And that's one of the reasons why we need to understand what scientific notation is and what it means, is so that we know what our calculator means when it gives us this E stuff. So, and again, when this is positive, that means you have a huge number because you're actually going to move the decimal 20 spaces back to the right. So positive means a huge number, and at the same time, the negative value means that it's a tiny number. So you're taking the understood decimals right, or you're actually moving it to right here, and it started right here. So you're moving it that much, 28 spaces. But since it was a small number, it's going to be a negative exponent. And again, if you're looking at this on your calculator, this would have been 9.1 e negative 28. And the negatives are kind of hard to see on the calculator. So if you do have an e, be sure to look closely to make sure whether or not you have a negative symbol on there. And here are two examples. So basically here we have the 0 and we're moving it 1, 2, 3, 4, 5 spaces. And it's a small number, so it's going to be negative fifth. And then here, if we were to put our decimal here, and we were to count the spaces, we would have 2 and then 3 and then 3. So that is a total of 8 spaces, and it's a big number, so it's going to be positive 8. So hopefully scientific notation makes sense to you. One other thing that is huge in terms of what students misunderstand, and I get why you do, because if we had an equation and we wanted to take the square root of both sides, we would have to take really plus or minus the square root of both sides. However, if you are told that you have the square root of 4, the square root of 4 is not positive or negative 2. The square root of 4 is always exactly 2. So if you're told the square root of 4, not x squared equals 4, that's something different. But if you're told the square root of 4, that's always going to be 2. And if you're told negative the square root of 4, that's always going to be negative 2. So do keep that in mind too. Again, if you're told x squared equals 4, that's when you would do plus or minus the square root of both sides. Again, that's very different from being told what is the square root of 4. So try to remember that. Here are a few more rules, and I think this is about it for the rules that we have. These rules have to do with radicals, instead of exponents, but they're very closely related actually. If we have a number raised to a power and then the root of that power, we can flip those around. And they've used, again, real number examples of being allowed to do that. And you're allowed to do it with real numbers, and so you are allowed to do it with letters as well. And so here uh, we can take the root first and then raise to the power, or we can raise to the power first and then take the root. If we have the same root, look at, they're both in. So if we have the same root, like the square root of a number times the square root of a number, or the cube root of a number times the cube root of a number, then you keep whatever the root was the same, and you can multiply the stuff beneath. The same is true with fractions. You can do the fraction first and then the root, as long as the root is the same. And of course, you're going to assume that the stuff in the denominator is not zero because you're not allowed to do that. If you have double roots, and so you have a cube root and then a square root, for instance, then you can take the 2 and the 3 and multiply them together, or the 3 and the 2. It'll give you the same thing, and you'll get the sixth root. So again, it'll always work with numbers. Here, the understood root is 2. If you don't write the root, it's understood to be 2. Again, here, these are second roots if they don't write them. So the square root is the second root, and then squared, that's really going to undo these. So the fifth rule is that if you're taking the nth root and raising it to the nth power, you're undoing them. But there is a caveat, and really, this should really be part of 5. And the caveat is that if you're doing this to um, an even power, if your n is an even power, then whether or not a was negative, you're always going to end up with a positive number because the square root always has to be positive. It can never be negative. That's because when you square something, you're multiplying a positive times a positive or a negative times a negative. And either way, you're going to end up with a positive number, whether a was positive or not. So remember that if you do have an even root, it's really the absolute value of a. Yes, they're undoing each other, but you end up with really the absolute value of a. If it's an odd root, though, you're really just stripping off the stuff. So raising to the power of and taking to the root of, they undo each other. And you can play with that with actual real numbers all day long to kind of confirm that for yourself. So here are some real examples with real numbers and real roots. So if we do the square root of 36, it is, and we could put that in our calculator if we wanted to, that is going to give us 6 because 6 times 6, or 6 squared, is 36. And then if we do the negative of the square root of 36, that's going to give us negative 6 because, again, you just can kind of take that out and do the same stuff that we did in part A, and you're going to get negative 6. If you have cube roots, again, cube means you're multiplying 3 times. So you would have on this one, you would have 5 times 5 times 5, and 4 times 4 times 4 would be the 64. And so that means that when you do the cube root, you're going to get 5/4. So hopefully all of that makes sense. If you have to the fifth power, negative 2 times negative 2 times negative 2 times negative 2 times negative 2, and these are all dots. Let me make sure that that's a little more obvious that those are multiplication symbols. So if you multiply negative 2 times itself 5 times, then you will get a negative number because it's odd. And so these pairs will make it positive and these pairs will make it positive, but we still have an odd number, an odd man out. And so we do have a negative overall. And then the numbers multiplied together will give us the 32. So negative 32. Now, this one is undefined because, again, we've got a fourth root of a negative number, and there is no way because when we have something raised to the fourth power, we will be able to pair it off. And so even if these are negatives, then they're going to be positive when you pair them. So this will be a positive times a positive, and so it'll have to be positive. So this one would really just say no solution on this one, not a real no real number solution. And then uh, so a lot of times we write these powers as fractions, and I think that's pretty cool. It helps me to be able to do the arithmetic, um, the, the radical arithmetic stuff, if I think of it as a fraction more. So I often, when I see this, will just convert it to this. So for instance, what this is saying is that 9 to the 3 halves is going to be, you can do either one first. So we could do the square root first and then cube. And that's usually going to be the best option to get it to be a smaller number first and then cube. So let's do that one first. So I'll do the square root of 9. And I don't have to write the 2 here because, again, the root of 9 is understood to be squared unless we write something else. And then that's raised to the cube power. So essentially I'm doing this first stuff here. And the square root of 9 is 3. So this is 3 to the third, or 27. Now, if I did it the other way, then basically, actually, let me do that in a different color. So if I do it this way, then I do the 9 to the third first, and then take the cube root, the square root of 9 to the third, then I get a really big number. It still works, but I get the square root of 729. And I had to do that one on my calculator to be sure that that was 27. Actually, I had to do the 9 to the third on the calculator too. Um, I like the calculator for arithmetic. I'm not actually really good at arithmetic, so I love the calculator. The calculator is my friend, and I encourage you to use it as well for the things that you can use the calculator for. And so that's really what this means, is that you can do either one. And then here are some examples here. So we could multiply these two together, and that's what I would do on this one. I would multiply these two together under the radical and then take the root. And so 8 times 2, that gives me the root 16, and that is 4. And then the cube root of cube, those will cancel each other out. That is our properties 5 and 6, and since it's odd, we know that it's just 5, because that's going to be 5 times 5 times 5 under the cube root, and so that's just going to be 5. For C, we also know under 5 and 6, and I would really look at 6 more than 5. So we know because it's odd, that's going to give us X. But for D, it's really the absolute value of Y that we would get, because we have the even option here. And so for D, we need the absolute value of Y. So hopefully all those make sense. And then simplifying radicals. So whenever you're asked in problems, and you will be asked in problems to simplify, to give answers in the simplest form, then these are the 3 things that you want to do. First of all, you want all possible factors to be removed. So if you have the cube root of 8, and you can simplify that into the square root of 8, you can simplify that into 4 times 2, where the square root of 4 is just going to be 2. times the square root of 2, then you definitely want to do that to get as much out from underneath, because the 4 can come out from underneath the radical, as you possibly can. And then we'll talk about how to do number 2 in just a second. So this is rationalizing the denominator. So if you have radicals, square roots or cube roots or anything in the denominator, you want to get rid of those and move those to the numerator. And we'll talk about how to do that. The index is what root it is. So we want that to be as reduced as possible. So there is no fourth root of 4, but there is a square root of 4. And so we can simplify this by thinking of it as 2 squared to the 1/4. And so that's the same thing as 2 to the 1/2. Again, basically they've converted this to the fraction form. So they had it in this form, and they've converted it to the fraction form. And again, that's really handy when you've got stuff like this. So converting it to the fraction form, and then you've got an exponent raised to another exponent, and the rules there say that you are going to multiply those two exponents together, and then you convert back to the standard form, which is just square root 2. So here are some more examples. Let's do one at a time. So for the cube root of 24, we know that we want to be looking for perfect cubes here, essentially. And so we know that 24 breaks down into 8 times 3, and 8 is a perfect cube, and that means that we can move that 8 outside of the cube. So that's one of the things that we'll want to do. 8 is 2 cubed, and we move the 2 outside of the cube. We have to leave the 3 in there because it's left over, and so we can't get rid of that. And then for the cube root of 48, or the fourth root of 48, you may have to use your calculator to kind of get the prime factorization of 48 going, but you'll realize that 3 can't be broken down, but the 16 is really 2 to the 4th power. So 2 to the 4th power can come out of the 4th, and so that'll be 2, and then the 4th root of 3. And then our 75x cubed, all under the square root. We know that 75 breaks down into 25 and 3, where 25 is a perfect square, but 3 is not and can't be broken down anymore. And then we want to make this a squared as well, so we have x squared, but that leaves us with the x. And so now our 25x squared can come out because those are both perfect squares, and we have 5x on the outside of the radical with our 3x left on the inside of the radical. And then for our next example, we want to do cubed roots. And so we think of 24, and what can we take out that's cubed? So 24 breaks down into 8 times 3. Again, 3 is a prime number, so can't break it down any further. But 8, fortunately for us, is a perfect cube. So that's good. We also want to make this a to the 4th a perfect cube. So that's a to the 3rd times a. And this is going to be the leftover part, and this is going to be the part that's the perfect cube that can come out. So when we take the cube root of the perfect cube, we are left with 2a on the outside, and then our leftover stuff underneath the radical. And then last but not least, I think it's the last one of these, we have an undoing. So we have to the 4th power and the root of the 4th. And so that undoing, did I copy? No, I didn't copy. But we would want to use the rules, and the rules back here state that if you are even, and we are here, then you're going to have the absolute value of a. So here we have the absolute value of our 5x. And that the 5 can come out, but it's still the absolute value of our x there. And we talked, so that was our first point, was to try to get as much out from underneath the radical as possible when we're simplifying. Our second point to simplifying was to rationalize the denominator. And there are actually two different ways to rationalize the denominator. So, two different types of denominators. There's a simpler part where you just have one radical in the denominator, and then there is a slightly more complex part where you have a radical plus a whole number, or maybe a radical plus a radical like we have here. So you have a more simplified denominator and a more complex denominator. But we can do both of them. We can rationalize both of them. So let's talk about the easier part first. So remember when we talked about, like, if I had any fraction, I could multiply by a over a as long as a was not 0. So we're allowed to multiply by the same things. So here we're multiplying by the square root of 3 over the square root of 3 because the square root of 3 is the thing that's in our denominator. So we're going to take what's in our denominator and we're going to multiply by exactly that same thing. But whatever we do to the denominator, we have to do to the numerator so that we're not changing the value of that, our original value here. Because this is 1, and when we multiply any number by 1, we are not changing its value. And so then we have 2 square root of 3 on the top, and we have the square root of 3 times the square root of 3 on the bottom, but the square root of 3 times the square root of 3 is just 3. And so we still have a denominator, but now that denominator is rational. In other words, it doesn't have any roots in it, doesn't have pi in it, it doesn't have e in it. It is a rational number. And so we have rationalized the denominator because it's now rational. Now, we'll want to do almost exactly the same thing for these complicated ones. We want to take exactly what's in the denominator and put it over here, except with one big difference. Whenever we have plus, we'll use minus. If we happen to have minus, we would have changed it to plus. So you, and this is what we call the conjugate. It's a fancy word. But the conjugate means it's exactly the same, except that you have changed the sign. So the sign is different, but all of the numbers are exactly the same. So the numbers are exactly the same, it's just the sign that is in between them is different. And when you do this, you have to FOIL it out. But when you FOIL it out, it turns out that the middle term drops out because the middle terms drops out because you've got this positive and this negative. So the fact that you've got a positive and a negative means that when you FOIL these out, and we'll talk about foiling more next time. So I believe it's next time. Certainly we will talk about foiling a lot more later. That's where you take the first and multiply it by the first, and then you take the outside 2, and then you take the inside 2, and then you take the last. So all of that is what foiling is, and we're not going to do that this time, but just be aware that the middle terms drop out because the negative and the positive. And so that's going to leave us with the square root of 5 squared and the square root of 3 squared, and both of those then become rational values, and we subtract those rational values, and that's going to give us a whole number so that we have a rational value in our denominator. Now, it moves the radicals to the numerator, but it turns out that we like that better than having them in the denominator. So again, that's the second step of simplifying values, is going to make sure that we have a rational denominator. And so we can do a couple of examples here. We would start with this one. We would just do square root of 3 over square root of 3. And so that's going to give me 5 square root 3 divided by 2 times 3, or 5 square root 3 divided by 6. Here, I would want to multiply by the cube root. Actually, I want to put this in fractions because this one's a little more complex. So let's say that this is 2, 5 to the 1/3 power. So this one's a little more complex than what we did on the previous one. We want to multiply this part so that we get just 5. So it turns out that we actually need to do 5 to the 2/3 because if you'll remember, when we have the same base, we add the exponents. And so 1/3 plus 2/3 will give us 5. So we really want to do 5 to the 2/3. So this one is, I'm glad we did this example because it is a little more complicated than the example that we did before. And whatever we do to the bottom, if we do it to the bottom, we have to do it to the top so that they stay the same because we're not allowed to just multiply willy-nilly. We have to keep it equal. And the way we do that is by saying this is really just multiplying by 1 because the numerator is exactly the same thing as the denominator. And when we do that, we will get 2 times 5. I'll just go ahead and write it as 5 to the 2/3 for now, divided by, and now we have 5 to the 1/3 plus 2/3, which is just going to give me 5 to the first. And then I will have 2, and I can write that as the cube root of 5 squared, or 25. And then I just have 5 in the denominator. And so that will be my final answer on this one. I could have left that as 5 squared, but I think it's better to go ahead and write it as 25 instead of 5 squared. And now we don't have a radical in the denominator, so we do have a rational denominator. And we can't pull this 25 out. We could if it were square root, but because it's a cube root, we can't pull it out. So there's nothing we can pull out there. And then last but not least, we want to do a conjugate one, right? So for this conjugate one, we would want to multiply by the conjugate. So we have 3 and then square root of 7, but we change the sign in between. And so what we do to the bottom, we have to do to the top. And I'm going to go ahead and FOIL this out to show you FOIL and to show you how things cancel. So our FOIL is our first terms. So I'll do the numerator first. 2 times 3 minus square root 7 divided by. So our first terms, that's going to be 3 times 3, or 9. And then my outside is going to be right here. So that'll be negative because of this negative right here. So that's going to be minus 3 square root 7. And then that was the outside. Now I want to do the inside. So the inside is going to be positive 3 square root 7. So plus 3 square root 7. And see how those fall out? And again, that's because we have the different symbols. So that made it fall out. And then the last term is going to be positive square root 7 times negative square root 7. So that's going to give me minus 7. Minus 7. And I'll go ahead and extend the division there. And so now I'm going to distribute on my numerator, and that'll give me 6 minus 2 square root 7. And then divided by, these will fall out, and I'll have 9 minus the 7, which gives me 2. And actually, I should have left the 2 factored because 2 times 3 minus the square root of 7 divided by 2. And then I can cancel those 2's out, and that's just going to give me 3 minus the square root of 7 as my final answer. So hopefully that all makes sense to you. I did a little longer than the slide previous talked about, just to show us that these middle terms do in fact cancel each other out with the conjugate, and that's why we choose the conjugate that way. Now, for all of these, when you come into class to do the class activities, we will work class activity problems together. Then the things that you'll want to bring to class with you are your lecture notes with your notes written on top of them. And so hopefully you've been doing that as you were going through this video. So you'll just bring those notes in. And then your formula card as well. There are actually a couple of formula cards, and I hope to give that to you on the first day of class, but it's also in D2L. So you can find that in D2L under the syllabus formula card section. And then if you have a laptop, then you can, use these as reference tools, your textbook as your reference tool. There's a link to the textbook in D2L. And then don't watch videos during class, but certainly for homework and before class, you can watch the content videos. There are actually additional videos that are embedded into the homework that you can have as well. So all of these things will support our class activities, and all of these things will support the homework. At the beginning of each class, I will let you ask questions specifically on the videos for that class. But if you have other questions, then what I want you to do is text me or remind me a message. And I'll answer those outside of class since our class time is so limited. And I think that's it. So thank you.